So we're going to be wrapping up our coverage of completion stage methods by going through an example case study. And we're going to do this in 2 steps. This particular example will be found in the EX8 project in my Java 8 folder and my live lessons GitHub repository. So we're going to demonstrate the use of a number of completion stage methods using this test fraction multiplications 1 method that's going to multiply big fractions using a stream of completable futures. And this will illustrate a couple of interesting things. It'll show you how to use these completion stage methods in interesting ways. It'll show you how to combine completable futures with streams, sequential streams, which is cool. And it'll also start to talk about arbitrary arity methods, although we won't cover that in detail here because we have that as a later lesson. So here's what the particular program does. It calls this factory method called make big fraction, and we'll look at that in a second. And make big fraction is going to generate every time make big fraction is called, it's going to generate a large, random, unreduced fraction, or big fraction. And we're going to use the generate method. This is the stream generate factory method. And generate will call whatever you pass it as a lambda expression, and it'll just call it forever. But we don't want the program to run forever. So what do? We limit it to S max fractions number of items. So make big fraction when called with generate will go on forever, but we stop after some number. Let's say it's 100 or 10 or 50 or whatever. Here's what make big fraction looks like. It's a pretty cool factory method that creates large and random big fractions, and I mean really, really large random big fractions. So you can see here that it is going to take a random number generator and a Boolean to indicate whether we want to reduce the big fraction or not. We call big integer with its constructor passing in the random field, random parameter, which says make a random big fraction. And we want to have the random number distributed over the range 0 to 2 to the 150,000th minus 1. And I think you will agree that's a really, really big number, or it could be a really big number, which is why we're using a big integer, because big integers can be arbitrary precision integers, and they can be mammoth. And if you run this program, you'll see you get huge results. So we create ourselves a gigantic numerator, and then we go ahead and we create a denominator which takes the numerator and divides it by some random number between 1 to 10. So we're going to have a smaller denominator, but it won't be 0, thankfully. And then the last thing we do is we return a big fraction that will have that numerator and denominator, and then we'll either decide to reduce it or not. In this case, we are not going to reduce it because that's going to be done asynchronously by a different part of the stream. So the next thing we're going to do is we're going to use the stream map intermediate operation, and we're going to pass in a function as a local variable. We'll look at that in a second. And that's going to reduce and multiply each of those big fractions asynchronously. So let's go take a look at that. This is that function. It's called reduce and multiply fraction. And you can see it takes a big fraction, which is that randomly generated large big fraction, and it's going to return a completable future to the result of reducing and multiplying said big fraction. So here's how this works. We use our completable future supplyAsync factory method, passing it in a supplier lambda that will reduce the unreduced big fraction in the background in a thread from the common fork join pool. So that'll put that computation in a queue and run it in a thread in the common fork join pool. And then we use thenCompose to take the result that reduced the unreduced big fraction, and it will then go ahead and asynchronously multiply it by some constant. And you can see it's asynchronous because we use the supplyAsync factory method a second time. We used it up here, and then we use it again down there to run that in the background. Now at this point, if you were, and so the reason we use thenCompose in this particular context is because we want to ensure we only have one level of completable future nesting. If we use thenApply, we'd end up with completable future to big fraction, which is ugly and unwieldy. But if you were paying attention in the earlier discussion about the variance of thenApply and thenCompose, you would know that you can simplify this even further by using thenApplyAsync, which allows us to avoid having to call supplyAsync a second time, but still get the results of denesting and having this computation run in some thread in the common fork join pool. So a nice clean way of doing that. So that's what we would use for this particular implementation. This outputs a stream of completable futures to async operations on big fractions. So think about this for a second. We've got a stream of big fractions up to some limit. We then map this particular function, and that will create us. It'll go from having a stream of big fractions to a stream of completable futures to big fractions, who are all off running around in the background somewhere doing their thing. And that's where we're going to end this particular part of the lesson. And then in the second part, we'll talk about the rest of what goes on after that here. So that's part 1.